We know that the performance of LLMs for texts is pretty good, but in the case of temporal data, it is not so good. So because of that, we have to solve that problem. But there's a new breakthrough that actually addresses this problem pretty well. And let us talk about that breakthrough. And this is a meme that ARIMA, you might have used ARIMA, LSTMs and stuff like that, transformers, and just ask ChatGPT. Let us start from the fundamentals because I like talking from fundamental. What is time series data? Time series data is basically a collection of data in which in x-axis you have time. So what is actually the state currently? The state is that LLMs absolutely suck for time series data. And another thing is that LLMs take so much VRAM. So let us consider this particular case. You have your heart rate data of the time when you are actually sleeping, and you have your heart rate data of the time we actually walk. So at that particular time, if you give your LLM to actually understand whether you are sleeping or not, it is going to be so difficult if you use ChatGPT because it's going to cost so much. But the task is so simple that a very simple calculation can actually do it. Because of that, we want this to solve it. There are two ways of solving this problem. So one of the problems is just put the data in the prompt, which we were doing and we were failing. But the thing is that we have to put the data in a certain form, which is actually understandable for LLMs or processable for LLMs, for which the LLMs might work good. It's like one-shot prompting, two-shot prompting, that kind of thing. So this is how we can actually do in one of the cases and giving the prompt pretty good. And this is a fancy architecture, which is basically a fancy way of telling, copying and pasting the data and asking the LLM. And another way is basically representing the data as native modality. So what is that? You know about image-based LLMs, multimodal LLMs, right? They can understand image, but they do not copy and paste each and every pixel of the image in the text itself. What it actually does is like cross attention or something like that. So what is cross attention? We have to figure it out. So in order to figure it out, let us look at what is cross attention. And before that, we have to look at what is self attention. So attention is all you need. This is a paper from 2017, which is the breakthrough for LLMs into existence. Because of this paper, we actually have the attention, the method by which we have solved a big problem that was there for computer systems or AI systems. So this is what the problem is. Let us consider a simple sentence. The animal did not cross the street because it was too tired. This is the sentence. Now there is a pronoun it, there is a name animal, there is another name street. The thing is that in previous computer systems, this particular context which this it is referring to was a little bit difficult. But in 2018, because of this paper, it all changed. And it basically gave a method to understand the context. So what it actually does, the main question that we have is that how LLM actually understands your prompt or your query or your text or whatever the thing is. So what it actually does is it creates pair of words, right? For each of the word and maps it to each another word in the prompt and tries to calculate context. It is called the attention weight. Let us consider in this case, the query is it, right? We need to know what it is actually associated with. And another thing is key. So we have a query it and key is animal, any other word, right? So it matched with animal. It is calculated how much is the relationship between it and animal. If it is very high, then it is going to be, okay, it is associated with animal. Now, how this is calculated? It is calculated by the LLMs, by the neural networks. You actually train it to calculate, right? So this is done with the help of training, and it all happens in the vector space, right? So it with the street, and similarly, very low. So if it is very low, then okay, it is not the case. It is not related with the street. And if it is related with tired, then it's medium. So maybe it is actually related with tired and animal. That is how LLM actually understands it, right? And let's talk about cross attention. This is basically self attention, just doing in the form of texts. Now, what it was happening in the first method, that our whole prompt of time series data was actually inside of the whole prompt, right, in the text prompt itself. And what it happens is that for each and every token, this particular thing is done, because of which VRAM uses this skyrockets very easily, right? Because the complexity, even the increment of complexity of this for loop or something like that, it does not work exactly the same way, but you can see from the higher level that it works this way. O n square complexity is there still, right? So it is really complex. But in the case of cross attention, what you can actually see is that we basically represent the time series data that we've got into a different format so that we can make the LLM understand in the vector space itself. So you have time and you have value. So the prompt that we actually are having here is this increasing? Is this value with time is increasing or not? That is the prompt. So the thing is that it calculates key and value. Key is basically the time, the feature representation by the LLM for time, and value, it is for the value itself, right? So this is what we have, and there is a query. So this increasing is going to be translated into a query. It is also a vector for the key, right? Now, after that, what we actually do is computer score. We basically ask the question, doing this dot product means that we are actually asking the question, which of the time frames are going to be relevant for our calculations. So for the third time frame, it is showing that it is extremely relevant. So because of that, we take that into consideration. We do softmax. Basically, this is the softmax operator. It basically runs it from 0 to 1 for the whole thing, right? And like this one has 90%. It is like 0.91. So because of that, it is highly contextual. It is the most important data that you can see here. And going further on, in the latent space, this is what it is calculated. Now, this particular representation, which is actually done by this particular block in the architecture, that is perceiver resampler, what it does is yields a fixed sized latent representation of whatever the time series data was, and then blocks it into the pre-trained LLM. In the previous time, what it was is that here itself we plugged in the time series data, but in this case we actually plugged in the representation of the data, right? A certain representation of the data in a similar way, which the multimodal image understanding models actually do. It is in the similar way. So this is what it is done here. And then after, it shows a really good results. If we look at the results, the main thing is the memory users. There is a better F1 score as well. It is like 60% F1 score for gated cross attention model, and for the soft prompt model, which is basically the other one, 20% around. So it is 60% and 20%, pretty good improvement, I would say. And like you can see the memory users as well for Gamma 3, 270 million. In soft prompt, what happens is that if the sequence length increases, then this one increases exponentially, kind of exponential, right? And for LM, Llama and other models, it does not work basically. So because of that, we can conclude successfully